When updating state and publishing an event, two separate systems are involved, the database and the message broker. If the database commit succeeds but the network fails before the publish call, the event is lost forever. This violates transactional integrity, leading to inconsistent microservice states across your system boundary. The Transactional Outbox Pattern is the definitive architectural solution. It guarantees atomicity by ensuring the event storage and the state change occur within a single database transaction, eliminating the window of failure inherent in the dual write problem. The core mechanism involves adding an outbox table to the service database. This table stores the event payload, destination topic, and essential metadata. A robust schema requires specific columns. Use a universally unique identifier for the event identifier, which is essential for later idempotency tracking by consumers. Include a timestamp for ordering, the destination topic or queue name, and a status field, typically initialized to pending. The payload must be stored as a serialized string, usually JSON, ensuring schema evolution is manageable. Indexing the status and timestamp columns is critical for efficient polling. The application code must insert the event record into the outbox table immediately before committing the business state change. This insertion must happen within the exact same database transaction scope as the state modification. For example, if updating an order status, the event insertion is the final write operation before the transaction commit. Since both operations are part of the same ACID transaction, the database guarantees that either both succeed or both fail. This is the fundamental mechanism that solves the atomicity problem. The relayer is a dedicated, separate process responsible solely for monitoring the outbox table. It operates outside the main application transaction boundary. Its primary function is to select pending events, publish them to the message broker, and then update the event status in the outbox table to published. This separation of concerns is vital. It prevents the message broker latency, which can be high, from impacting the core business transaction response time, ensuring low latency for user-facing operations.
Efficient polling requires careful query design to handle concurrency and high throughput. The relayer should select a limited batch of pending events, ordered by timestamp. In multi-instance deployments, use a pessimistic locking mechanism like select for update skip locked, available in Postgres or similar databases. This prevents multiple relayer instances from processing the same event concurrently, avoiding duplicate publishing attempts. After successful publication, the relayer must execute a separate transaction to mark the batch as processed, ensuring the status update is atomic. While the outbox guarantees zero lost events, the relayer's network retries mean the same event might be published multiple times. Consumers must implement idempotency checks to achieve exactly once processing semantics. This is achieved by storing the incoming event's universally unique identifier in a dedicated consumer state table. Before processing the event payload, the consumer checks if that identifier already exists. If the identifier is found, the event is silently discarded. This guarantees the side effects occur exactly once, regardless of how many times the event is received. If the relayer fails to publish an event due to broker unavailability or network errors, it must implement an exponential backoff strategy before retrying. This prevents overwhelming the broker during transient outages. After a predefined number of failed attempts, typically 5 to 10, the event status should be updated to failed. These failed events must then be routed to a dead letter queue topic. This mechanism prevents a single problematic event from indefinitely blocking the processing of subsequent events in the outbox table, maintaining flow. Polling the outbox table introduces inherent latency and places continuous load on the operational database. Change Data Capture, or CDC, offers a superior low-latency alternative. Tools like Debezium monitor the database transaction log, or write-ahead log, directly. When a new record is inserted in the outbox table, the CDC connector immediately streams that change to the message broker. This eliminates the polling overhead and provides near real-time event propagation, making it the preferred choice for high-volume, low-latency systems.
The outbox table is append-only and grows indefinitely, which will eventually degrade polling performance. Regular maintenance is mandatory. A separate scheduled job must periodically delete records marked as published or failed that are older than a defined retention period, typically 7 to 30 days. This archival process ensures the relayer only scans a manageable subset of recent events, maintaining query efficiency and preventing storage bloat. Retention policies must align with regulatory requirements for audit trails. Implementing the Transactional Outbox Pattern requires careful coordination between the application code, the relayer process, and the consumer idempotency logic. While it adds complexity compared to simple direct publishing, It is the definitive architectural solution for achieving reliable event sourcing and communication in distributed systems. This pattern guarantees that no business-critical event is ever lost due to transient infrastructure failures, providing the foundation for highly consistent microservices.